Okay, so we're going to be going over composite functions. So they've given us essentially two functions here, and they've asked us to build a composite function, and in that same process, what else do they want? Get the equation, to graph it, and the domain range. Okay, so the very first thing we're going to do is build the equation of this. And this is very similar to our function notation. So it's actually common for them to maybe even call this h at x, right? To use the same variable, our new function, you give it any random variable to define it, and h at x is equal to the function of f at x with g at x inside. So what we're going to be doing here is we're taking this function g at x, which is this value here, and we'll be plugging it into any of the x variables of our f at x function. Okay, so this is very similar to if g at x was maybe just equal to, let's say we gave it a letter, maybe something like b, right? Maybe we call this function b is equal to all of this. Well, then what this would be is essentially we'd be finding f at b. Okay, so that's what we'd be doing. So since b is equal to that, we'll be plugging that in for everything. So what I'll do is I'll plug in the function first to show you the function notation, and then we'll plug in what's equivalent of it. So we take our f at x function, and I'm going to rewrite that out. So we get f at x is equal to x squared plus 3x. Okay. The next thing we're going to do, the next thing we're going to do is we're going to replace the x's in the equation with g at x. Okay, so there's one step at a time. So I'm actually going to write g at x in for each of those. Okay, so we have f at g at x. Okay, so you notice g at x, and actually I'll use a different color just so we can differentiate. This would be our g at x, right? So what happens here is, so those buttons aren't working up there, so I have to go in and out every time. But this x function is now replaced with our g at x, and we know it's squared, okay, plus 3 times, and we replace x again with our g at x function. Okay, and then from there, the next step is to actually replace or put in what g at x is equal to, so the actual linear equation. So we're going to replace our g at x's with our x, or 2x minus 5 in this case. Okay. So I guess I'll put that color blue maybe. Okay, so we're going to replace, oh, that's odd. Oh, there you go. 2x minus 5. So we'll replace that g at x. So I'm going to leave it as g at x in the function notation just because I don't want to write f at 2x minus 5. It just becomes tedious to write in there. And that's also how they represented it, at the g at x within f at x. So we'll keep it that way. Okay, so we're going to replace that part. So we get f at, and we'll just write the g at x in black now, is equal to, and now we're going to replace that the g at x with our 2x minus 5. Okay, so that our brackets are still around that, and it's still to the power of 2 plus 3 multiplied by, and again, that linear function we put inside, 2x minus 5. Does that make sense so far? Okay, good. All right, from here, we essentially equate everything. So I won't write out the left is redundant, it's going to stay the same. This becomes a function that has to be multiplied by itself, and we're going to collect our like terms after. So we have 2x minus 5 multiplied by 2x minus 5 because it's squared, and we have to distribute our 3 to each of those terms, which we can do in one step. 3 times 2x will give us positive 6x, and then minus 15. Okay. The next thing will be the distribution property of this. Okay, so we've done that, and the next thing is FOIL. You're familiar with?
Yep.
Yeah, so 2x times 2x will give us our 4x squared. 2x times negative 5 gives us our negative 10x. Negative 5, again, gives us the negative 10x. Thank you very much. And negative 5 times negative 5 gives us our positive 25. And we still have our other terms that we include on it. Okay, and then from here we just kind of collect our like terms. So we have 4x squared. Negative 10x is negative 20 plus 6 will give us negative 14x, and 25 or positive 25 minus 15 will give us positive 10. Okay, so we now have our quadratic function. So this is it, and this is, and I'm going to call it a new function. We're going to call it a new one. They called it y, or we could call it h at x, or y is equal to essentially the same thing here. Okay. That was the first step. The second thing, they wanted to graph it. this is just a quadratic equation. So we might be able to factor. Let's see if we can quickly factor. I'll common factor out 2. And I think that'll give us 2x squared minus 7x plus 5. Okay. And then if I find the factors of the first and last term, you're familiar with that style? Yeah? Okay. And we make 7? Yeah, we can make 7 here, it looks like. We have to make negative 7, so if they're both negatives, that'll give us negative 7x, and that'll give you negative 2, negative 5. Perfect. So I did a very quick style of factoring there. We put our 2x in one and our x in the other, and we had to do the 1 times negative 5, so it goes in here, and this goes in here. Did I do that too quickly?
No, it's fine.
You're okay?
Yeah.
Okay, so we factored it quickly, and that'll help us find our x-intercepts, right? Another thing we could have gone from there is we could have completed the square to find it in vertex form, whatever you're more comfortable doing when coming to graph. It's up to you. So that's going to give us we can find our x-intercepts very quickly. If we set our y equal to 0, we know that our 2 can cancel out, and we're going to set each of these equal to 0 themselves. So we split the equation. Still okay? Okay. 2x minus 5, 0 equals x minus 2. And we'll get 5 over 2 is one of them, and the other one is positive 2. Okay, so if we go to graph it, let's just say equals. Positive 5 over 2, so 2.5 and 2. So those are very close together, which would mean we can find our equation of our axis, or is it called axis of symmetry. Sorry, I was thinking of sinusoidal functions. Axis of symmetry is where we add the two values together. So it's essentially 2.5 and 2 and divide it by 2. So that's going to give us 4.5 divided by 2, maybe 2.25. I think that's right, right? Yeah, that sounds right. So that means our x value of our vertex is going to be at 2.25. And we can plug it into the original equation. I'm going quickly through the quadratic stuff. We can plug it into our original equation to find out. So we'll take our h at x, we'll call it h at 2.25. And our equation said 4x squared, I think plus 14, minus 14 plus 10. Minus 14x plus 10. So we can plug this value in. I'm going to quickly do it on a calculator to find out the y value of our vertex. So that would be 2.25 squared times 4 equals that value, subtract bracket 14 times 2.25 end bracket, okay, equals, and then plus 10, yeah, makes sense. Okay, negative 1.5, 1.25, sorry, so yeah, negative 1.25. So from all the info we gathered, I'm just going to do a very rough sketch of this here. Okay, but we found out that our vertex was at, let's give it a point. If this is 2 and this was 2.5, those were our two x-intercepts. Our vertex was directly between it, and if that's 1, it was at negative 1.25 and 2.25. I should write those better coordinates. So essentially, these are our major points of our quadratic. Does this make sense? Mm-hmm. And what was the last thing? And give it a domain and range. Okay, so since we have this, because it's quadratic, our domain. Do you know what our domain will be in this case?
X is all real numbers.
Yeah, that's right. There's no restriction. How about our range?
X must be greater than or equal to negative 2.25 or negative 1.25.
Yeah, y must be greater than or equal to negative 1.25. That's right. The range is it all exists above that value. Okay, so I did the second part pretty quickly because really we were focusing on the composite